Hello, it's Dave Giles here for the next lesson of IGCSE Cambridge International Education Physics, and today we are looking at Ohm's Law, part of the electricity and magnetism unit. And I want you today to describe and calculate EMF, electromotive force, and PD, potential difference. And I want you to describe resistance and use the Ohm's Law equation. So for a lamp to light up, there must be a battery to provide energy to move particles on a complete loop, no breakages allowed in the loop, which we have covered previously. In an electrical circuit, without a power source, the free moving electrons are moving at random. So you'll have some moving left, some moving right, some moving up, some moving down, but there'll be no net movement. So for example, you might have one moving at, say, 3 meters per second. That's not a realistic speed, but 3 meters per second left, one moving at 3 meters per second right. The average out is 0 meters per second. So there is no net movement of charge. When a power source to the battery are used, energy is provided to the free moving electrons like this. So you can see they all line up and they go the same way. Another way to put this, there is a difference in potential between points A and B, hence the name potential difference. Electromotive force of a power source is defined as the energy provided by a source to move 1 coulomb of charge around a complete circuit. A complete circuit bit is key. And generally, we talk about EMF, we talk about a battery or cell or power supply. So this one here is a battery, and it's 9 volts, or the cell, sorry, provides 9 joules of energy for every 1 coulomb of charge to move around a circuit. So potential difference across a component is defined as the energy provided by a source to move 1 coulomb of charge across the component. So they are similar definitions. So here, I've got a 9-volt battery, because it's 2 cells in this case, and these are 2 bulbs, and assuming you have the same resistance, that will be split evenly across the 2 components. So 4.5 volts here and 4.5 volts there. So very, very similar terms, potential difference in EMF. Let's compare them. So they both refer to energy provided to 1 coulomb of charge. They're both measured in volts. The definition is slightly different. The energy provided for PD, potential difference, the energy provided by a source to move 1 coulomb of charge across a component, whereas EMF is the energy provided by a source to move 1 coulomb of charge around the complete circuit. So there's a slight difference in definition there. And the EMF, so potential difference is always going to be less than the EMF or the same. Okay, so if you've got multiple components of the EMF, so it will be spread across different, the potential difference will be spread across different components. Whereas EMF is the maximum potential difference in a circuit. So let's have a look at some paper 2, the formula. V is W over Q, so voltage is work done over charge, and we use letter E for electromotive force. So let's have a look at some past paper questions. What is the unit of EMF? Easy one to start us off. It's the volt. What is EMF? It's work done divided by charge. How can 1 volt also be expressed? So it's 1 joule per coulomb, so D. The last one, in a circuit shown, 20 joules of energy is dissipated by the cell in driving 8 coulombs of charge around the circuit. What's the value of the EMF of the cell? So you just do EMF is energy over charge, 20 over 8, so 2.5 volts. So there's some paper 2 questions to cover the first learning objective, describe and calculate EMF and PD. The second learning objective, describe resistance and use the Ohm's law equation. So as electrons are pulled across the wire, the atoms block their path. This decreases the current. We call this resistance, and it's measured in ohms. So you can see here, these small things here are electrons, and the orange ones are copper atoms. And every time the electron hits a copper atom, it's encountering resistance along its path. Ohm's law states that the current and voltage are proportional, provided the temperature remains constant, and we'll look at more at the temperature side of things in a later video. Ohm's law relates voltage, current, and resistance. So resistance R of an electrical component is its opposition to the flow of charges. The greater the resistance, the more difficult it is for charges to flow. Hence, current is low when the resistance is greater. Think of it as a man running, and then the resistance here being the brick wall in the way. He'll have to jump over it. Another way to think of it is like this. Current is flowing around the circuit. You've got voltage trying to basically push it around, and then you've got resistance, which is making things harder for it to flow. Making it harder for the current to flow, rather. So in equation terms, you've got voltage is current times resistance. You can rearrange that. I get current is voltage divided by resistance, and resistance is voltage divided by current. Voltage is measured in volts, current measured in amps, or I use the full term amperes, but everyone just says amps. And resistance is measured in ohms. Just to point out, we use letter V for voltage, I for current, and R for resistance. So calculate the missing variables X, Y, and Z for each of these. Okay. So here I is V over R, current is voltage over resistance, trying to work out current. 10 volts over 100 ohms, 0.1 amps. Here, we've got resistance and we've got current, and we're trying to work out the EMF or voltage. So V equals IR, voltage is current times resistance. 0.5 times 100, which is 50 volts. And this one here, tiny bit harder. We've got 20 MA into little m, which means milli, or times 10 to the minus 3. So I'll convert that to amps. So it's 20 times 10 to the minus 3 amps, or 0.02 amps. R is V over I, 120 over 0.02, which is 6,000 ohms. Okay, so that's a very straightforward example of Ohm's law. Slightly harder one is when you've got more than one component, like this. So here I've got 240 volts of EMF. I've got two resistors. One's 25 ohms and the other is 35 ohms. And a typical question might ask you to calculate the voltage across each resistor, or say the potential difference across each resistor, or the current through the circuit. So we'll do that. And first thing you need to do is calculate the total resistance. So it's in series. We just add the resistances up. And next lesson, we'll look at what happens when it's in parallel. But for now, we'll just look at series. So it's RT is resistance total. Is R1 plus R2, 25 add 35, which is 60 ohms. To get the current, so I is V over RT, so voltage or EMF over total resistance, 240 over 60, which is 4 amps. And the voltage across each resistor, so across resistor 1, so V equals I times R1, so it's 4, times the value of R1 of 25, which gives me 100 volts. And the same process for resistor 2, V2 equals I times R2, 4 times 35, which is 140 volts. You can do a quick check. Add these together, 100, add 140. So the sum of potential differences should equal EMF, 100, add 140, 240, which is the same as the EMF. We'll have a look at some paper 2 questions now around Ohm's law. A pupil measured the potential difference across the device and the current in it. Which calculation gives the resistance of the device? It's potential so V equals IR, and we're trying to work out V, so V equals, V equals IR, and we're trying to work out R, so R is V over I, so potential difference divided by current, so it's C. 6-volt supply is connected in series with an ammeter and a 4-ohm resistor. What is the reading on the ammeter? So here we're going to do V equals IR, so I is V over R, so it's 6 divided by 4, which is 1.5 amps. An ammeter is used to measure the current in a 300-ohm resistor. The ammeter is shown below. What's the potential difference across the resistor? So the current here is 6 milliamps, so that's 6 by 10 to the minus 3. Remember, V equals IR, so it's 6 times 10 to the minus 3 times 300, which gives me 1.8 volts. Next question. So the last 3 were from paper 2. This is one that I've made up because it was... So what is the potential difference across the 2-ohm resistor? So it's 8 volts. The way I did that was V, I worked out the current first. So I did total resistance is 5 ohms. I is V over R, 20 divided by 5. So that gives me 4 amps. Then I did V equals IR. So 4 times 2 ohms, which is 8 volts. Now here, I deliberately use this picture because sometimes you might see it when you're doing some revision. Now this symbol here is the oldest picture for a resistor. And some countries still use that picture, that circuit symbol for a resistor. So what's the potential difference across the R3 resistor? So R3 is 15 ohms. So we need to work out total resistance first. 15, 15, and 30, 60 ohms. Work out the current. I is V over R, so 120 divided by 60, which is 2. And then to get the voltage, so the potential difference, you do V equals IR, so 2 times 15 gives me 30 volts. Now you can also do this using a potential divider equation, which we will look at in a future lesson. But for now, just talking about how to do it using Ohm's law. The next lesson will be resistors in parallel, which I will be uploading soon. Thank you very much, everyone, and I'll see you in the next lesson. Thank you and goodbye.